We are recording. Um, but the homeworks I set there, it should be 2 tries. So, the first time you go through and really bombed it or something, you do get a second chance on it and everything. I don't want to punish everybody. But so today we are going to take a look at chapter 15 and our introduction to capacitors. And Frenzel goes through and he does a decent job. He introduces the capacitor, shows kind of what the materials, what they're made of, um, what we can do with them. So we'll try the like tomorrow's lab. It'll be a simple one again, introducing capacitors, and we'll play around with them a little bit, see what the properties are and that kind of thing. I mean, our real eventual goal, basically through this class, I mean, one, yes, we're going to get into the AC analysis, right? So we're going to be studying the sine wave and how that interacts with components and such. The other side of the coin of that is the components that we're going to be looking at. I mean, you've been working with resistors up to this point and that kind of thing. But now we're going to introduce capacitors and inductors. Excuse me. So that way, and we'll be looking at, I mean, the end goal of this class is really to be looking at like RC circuits, which is resistor capacitor circuits, RL circuits, which is resistor inductor circuits, and then a combination where it's RLC and why we use those. Um, and there's a couple of different, actually, some interesting applications. And they're fairly, I mean, as far as components go, there's not a whole lot to them. I mean, you don't have, you're not like populated with a gazillion different things or anything like that. And they have them in different configurations where, and you'll recognize where, yeah, we do the series style configurations, parallel and series parallel configurations, and how and how capacitors and inductors are going to react to that and what they do. So with that being said, let's go ahead and take a look at the PowerPoint slides here. Pull this up. And there we go. So chapter 15, capacitance. And so what do we be looking at? So in the beginning, like I say, he goes in and talks about, we're going to talk about like what the capacitor does, what's it's made out of, that type of thing. So we'll examine that. And we'll take a look at like typical capacitors, electrolytics, the ultra capacitors, and then yeah, parallels and series, and how they work. And so the first approach we're going to really look at is just like we did before with a DC style analysis. So that way we get our understanding in and get used to working with the components. And then we'll introduce like the AC reactance of it all a little later, do our building blocks, right? So, and they make these out of a few different materials. You might have noticed that some of the capacitors are in different styles. You'll get some like in your kit where they're like little metal canister styles, and those are electrolytic types. And then there's different styles. They have like little round circular looking ones. They're like a mylar material inside of it. So when they talk about the dielectric, it can actually be, a few different materials that acts as a dielectric. Excuse me again. But the dielectric is essentially an insulator. And what's an insulator? It essentially likes to not accept a charge, right? Oh, so they did some interesting things with these, and they've been playing around with them a long time. I mean, this goes back to like the very early days of electronics, vacuum tube days and whatnots. And of course, then the styles looked a lot different than they do now. And they call them condensers back then, but now, yeah, now the newer styles, we call them capacitors. But what do? They And an interesting thing, they sort of act like batteries. I mean, a good way to like image it is to think about it like, it stores a charge, not indefinitely. Like a battery will store a charge for an extremely long time. The capacitor, well, I don't want to say it exactly like that. A capacitor can actually hold a charge for quite a while if you do it right. But so the capacitor basically will sit there and it'll store a charge. You can exceed the charge if you have a voltage applied across a capacitor that's more than what it can handle. Um, in some cases, they will explode. Some cases, they just burn up and make a lot of smoke and smell extremely bad. But yeah, if you do exceed the voltage rating on these things, they will degrade. The dielectric breaks down, and then it's anybody's game. But so when we measure how much charge can be stored by these capacitors, that's what they call capacitance. And the way they measure that, and we'll go on here, um, is basically the unit of measure for capacitor is what they call a farad. Farad. And this was another guy way back in the day, that in the early deals of electricity and whatnot. And in fact, you'll find many of the names that they do have for like the units and whatnot are actually named after pioneers in the electric field. But anyway, so if we go and apply a voltage to a discharge capacitor, what happens is that it causes a current to charge the capacitor. See, now an interesting thing with capacitors is a good way to think of it is they oppose voltage and typically allow current to pass through, which is an interesting concept. Um, but yeah, they block voltage. So voltage just doesn't go through like it does with a resistor. A capacitor will block the voltage. It says, "Oh, hold on here." It's sort of like a stop sign. Hold up, wait. We're not gonna let you through quite yet. And then he stores that charge and he reaches the full potential. So if I had like a 10 volt supply hooked up to just a capacitor by itself, okay, and this is a DC supply, so you have a positive and negative terminal to it. Um, what it will do is it'll charge up to the full potential of what I'm applying to it. In this case, like the 10 volt, as long as it can handle that 10 volts. Now, if I were to have like a smaller rated capacitor, let's say the capacitor I hooked up could only handle like 5 volts, and I hook up a 10 volts of power supply to it, I will exceed what the storage capacity is of the capacitor, and it will break down the dielectric. And like I say, it'll do something destructive. But they work uniquely. The two wire leads that you'll see coming out of the capacitors, when you look at it internally, they are not connected at all. They'll be separated. And then between the two will be the dielectric material that's used for that. And they're different from capacitor to capacitor. Some have like a mylar dielectric material within it. Um, like the electrolytics, if you were to open it up, it almost looks like a roll of paper, but what they have, it's like a shellacked material. So the dielectric is coated on that, but you'll see it's all rolled up. And so in the beginning of this thing will be one wire lead, and then at the end of the curl is the other wire lead. So the dielectric does separate it in between. So then what the capacitor does is, yeah, it concentrates that electric field, that storage charge in between those two and holds it there. And depending on the material and depending on how much of the material it is how it will do that. Like how much charge it can store and for how long type of situation. And here we see a little breakdown of it, right? Um, so essentially you would have, like in a case of like the smaller disc style ones, you would have the dielectric material in between. They might have the wire leads going up into it with little metal plates attached to that. And so you'll see that. And so essentially here we have a DC supply, right, hooked up to this thing. And then when we turn it on, essentially all the electrons are going to, they're going to go racing through. But again, like I say, the capacitor is going to stop that flow of electrons and do a buildup of them. And he goes through and yep, the two main effects of a capacitor are to charge and to discharge. So if I were to hook up like a straight DC supply to a capacitor and I apply my voltage, it'll reach the charge potential, like in this diagram, in this case, we have the 10 volts. It'll reach that 10 volts, but because of the polarities of this thing, it would reach the charge potential and then never release it. It would have to have a way to discharge it. So in this case, like, see how he has the switch on there? Okay, if I close the switch, I allow the capacitor to charge up to its potential. And depending on the rating of it, basically how much dielectric is in there, is how long it would take to store, because it's not instantaneous, okay? So each, depending on the size of the capacitor, it could be a very small amount of time till it reaches its charge potential, or it could be a longer amount of time. It really depends on the capacitor and the rating of the capacitor, and we'll get into that and see how we can figure out what the time constant involved with that would be. So, and basically that would be based like on our rating. So if I said, oh, you have a 10 microfarad capacitor, it's like, oh, okay. So then we can juggle around with that and see how long it actually would take for that 10 volts to reach its like maximum charge potential. And and in this case, like if we have just a straight DC supply, it'll continue charging until it equals the applied voltage, or it'll try to equal the applied voltage as long as it can handle that. If it's exceeding it, yeah, that you basically will destroy your capacitor. Oh, excuse me. Oh, all right. So really, the way to really look at this thing, right, is just always remember it's going to be charging, discharging. And in this case, when we have the DC supply, well, we'll get into that a little bit, but you would have to provide it with a means to discharge. And in fact, this was it's kind of a little funny trick in a way. If you take no, I can't say it. But when I was in school, we could, if you got the two little wire leads on it, you could charge it up, and or it's like a really small, like 2 or 3 volts or something like that. You could zap somebody with it. It was kind of an interesting little way to learn how capacitors discharge. But anyway, um, so yeah, we look a little bit at like with electric fields. So I mean, okay. So the dielectric in and of itself is not polarized. It doesn't care. Okay, it says, oh, this is what I am, and I'm just gonna sit here and be idle. But now, when we applied a voltage to it, now it's going to react. Okay, and this is where we get reactance from. So when I do apply like an electric line of force through this thing, um, it's essentially going to cause this dielectric to do something that the dielectric really does not want to do. Okay, because I mean, essentially, an insulator's job is to block like voltage and current, right? In this case, we're going to tell it it's gonna try to block it, but um, with the electric field going through that, we basically force the electrons to accumulate and sit on there. It's like, oh, here they come, whether you like it or not, And the dielectric, it doesn't. It does not like it. And I'll be honest with you, and that's why it blocks voltage. So, so now comes the interesting thing of discharging. So if we wanted to discharge it, we would have to provide it a means. Okay, now notice in the diagram here, he has no voltage source. In this case, the capacitor could be considered as the voltage source for this particular circuit. So if it's like a fully charged, let's say it reached the 10 volt potential, it would sit there, and then if we gave it a means to discharge, it would give us that 10 volts, right? And it's not forever. And how long it takes is again basically based on the rating of that capacitor. Excuse me. So yeah, so when you give it something to work against, it will discharge. In fact, when I used to do electronics repair back in the day, I used to have one of the really big like so one of the I mean really big honking ceramic resistor, and I had two wire leads soldered onto it. And what I would do with it whenever I got an assembly, because sometimes you would get these really large capacitors, like where you have like a 250 volt capacitor or a 400-volt capacitor or something like that. And that's an extreme amount of voltage, okay? And if you get zapped with that, it is going to hurt a lot. So what we would do is whenever I start to work on it, just to be sure, you take this big resistor, and it used to be in my kit, in my toolkit. And so you just take the wire leads and just slap it across that thing. And you could do it with a piece of wire, but the piece of wire would take that instantaneous charge, and yeah, it could be a little destructive. But if you get a really large, like the ceramic resistors that can handle a lot of power, and just use that to discharge the voltage out of the capacitor. Because yeah, and it would literally store that charge. I mean, you figure somebody yanked this assembly out of a machine somewhere. It could have been down in like Arkansas, or Arizona or something, and they sent it back to the repair center. And and you figure the time involved with that, it's well over a week, and this thing's still fully charged. It hasn't discharged at all. And it's like, oh my God. But so yeah, you always have to be careful when dealing with these things. If it charges up and it has not been discharged, that voltage potential will be sitting there waiting. And but so the way they have that, it's like so essentially a dielectric. It sits there and like I say, it likes to block the voltage. And the way to look at this thing, so when you do have like a charge or discharge current going through it, right? It's flowing through the plates and whatnot. And that's why I say it'll block voltage, but it doesn't really block current so much. And it's a strange concept, I know, um, but yeah, the current will pass right through the leads and go on about its way and do what it's due and that kind of thing. But so for charging and discharging, essentially what you would have to do, so like if I had the battery hooked up to it, given polarities and charged up the thing, I would have to then provide it a means, like, and a way to disconnect the charge part of it, right? In this case, the voltage source, and then give it a means to dissipate. Like if I had a secondary circuit with switches or something like that, and then I closed that switch and allowed it to discharge across, say, a resistor or something, then we could, yeah, that would be one way to charge and discharge. And this is looking at it from a DC analysis. We're not going to be throwing any like AC in there quite yet, but it's good to get that concept in there that, yeah, the positive and negative, because AC has both, which we'll get into in a little later here. All righty. So the farad. The farad's a basic unit. Um, and again, it all depends. And we use engineering notation still, right? And if you look down at the bottom, these are very typical ranges for capacitors. Um, Usually microfarads, nanofarads, and yes, you can, and picofarads. The most common, like for electrolytics and whatnot, you usually see in the microfarad ranges. And then as you start going down to the disc styles where they use like a mylar or a different type of dielectric, the little small circular ones, they'll be in like the nanofarad or picofarad range. And so the way they look at this is 1 farad of capacitance, okay, is equal to 1 coulomb of charge. And Coulomb, again, another guy, pioneer of electricity way back in the day. But he gets a little thing named after him. And here's our formula. And this is an extremely interesting formula because this formula applies to anything that's able to store a charge. If you go walking across a carpet, okay, and you build up an excess of like static electricity, you're getting all these stray electrons from walking on the carpet, you know, your feet pulling up and down and separating the electrons from the carpet and transferring them to you. This formula applies to that. You literally actually be able to see what the capacitance of U is with the voltage that's being pulled up off of the carpet and literally find out how much charge potential you have, believe it or not. But this works with everything. This formula, we won't use it a whole lot. I'm be honest with you, but it is a good formula to remember. You know, Q is equal to C times V. So Q, the charge or the charge potential, if you will, is equal to the capacitive ability, right? The capacitance times the voltage. And then if we were to look down a little further here and measure it in joules, right? What's the energy and storage capabilities of this thing? You'll see here, yeah, energy is equal to half of, again, capacitance times voltage squared. And it's just basically, so this one, the very top one, is like basically figuring out charge potential, right? How much charge can it hold? And then this one here is how much is stored. Okay, so don't get the two confused. One is how much it can charge, and the other one is how much it can store. So it's like if I say if it can handle 15 volts or something like that, that would plug into this equation down here. But we won't get a lot into that, but it just helps to like visualize what do we have going on here. But anything that's able to store a charge, you know, charge potential, that formula works for, believe me. And that'd be batteries, capacitors, and any other material yourself. And in this case, I mean, because if you go walking across the carpet, you build up that charge. It doesn't dissipate, right, until you go up to, you know, to a family member or something and zap them, right? The dog. But that charge potential is sitting there waiting. I mean, if you walked across the carpet, went into the kitchen and whatnot, right? You still have that charge sitting there. It hasn't gone away. So, and that formula would apply to that anyway. So, so again, start looking through. We get, you know, to what the capacitors are, how much dielectric, and like I say, the different styles. They did a little different approaches on the materials that they used and that type of thing. But and it really comes down to it's like the ratings. Like I say, how much charge we can handle. You usually see the really large voltages will be the electrolytic ones, right? The big round can looking ones, like that big blue one I was running around with yesterday. Those are dielectrics. Dielectrics. Those are electrolytics. And for larger voltages, those are the common styles. Now, for like real small voltages, like electronics wise and stuff like that, that's why you'll see like a little ceramic looking disc and they have mylar material or some other kind of dielectric material inside of them. And they're pretty cheap. And so here we go through here. And so because it is made of a specific material, and see, he covers a lot of this that we're just, it's good to know. It's good to be able to understand how you know, what makes up the capacitor and whatnot. But for every material, it'll have a constant. So if we're dealing with, you know, specific dielectric material, like I keep saying mylar, right? So if we go and look up, we would actually be able to find out the properties of mylar, and it would have a constant. You know, mylar is mylar, no matter what you do, right? So when we deal with the relative permittivity of it, which is what the ability to be able to reject the charge, um, or in the way he puts it, the ability of an insulator to concentrate electric flux. What the hell does that mean? So what it is, it's like it's its ability to resist the voltage. Okay. And so, and it will resist it to a certain point, and it says, nope, nope, you're not getting through. And that's how they build up that charge potential, because that dielectric is not liking that voltage. It really does not. That's its job. It's going to sit there and it's going to fight it out with the voltage and say, no, you're not coming through. And then finally, the voltage reaches up to the full charge potential of this thing, and finally, the dielectric gives up and says, okay, fine, you win, and it'll sit there and eventually discharge it through. But yeah, the very bottom one here. Yeah, the voltage rating is important because if the insulator ruptures, it provides a conducing path through the dielectric. Yeah, and it can be destructive. In the case of electrolytics, they really don't like being exceeded. You'll see some different strange effects from them. So, and here we go. Here's a wonderful formula for you. But yeah, don't worry, we're not, this is just going to really be in this chapter only. It's just one of those things to understand, what's going on with it and that kind of thing. And then once you do that, we'll probably never look at this formula ever again. But this is basically how they figure out the dielectric constant, basically what its capacity is. And you can see here, well, the plate area. So the size is important. The material is important, right? um, and the spacing. So really depends on how large or how small they've made this thing. And then you can go through and plug in your information and find out, boom, okay, so what is my overall capacitance? And that's how they do it. So when you do look at them, that's what is going on. And here we go, this is better. So yeah, so if you look in the inside, so yeah, see ceramic, right? You wouldn't think ceramic, and it's like, well, ceramic's a dielectric. It's a good insulator. Plastic, plastic's a good insulator as well. We put like nylon insulator across our electrical wires to our homes and buildings and everything, right? It works pretty well. And then the very bottom one, paper. And you wouldn't think paper, and it's like, well, it's wood. Wood doesn't like a charge, right? So inside of, like I say, in the electrolytics, if you open them up, it is just like a. In fact, maybe I'll do that in lab tomorrow. We'll cut one open and take a look inside of it and take a look at the material. And here's a whole list. Now, interesting enough, believe it or not, the air vacuum ones were the condenser style units way back in the beginning. They actually used them this way with the vacuum tube technology. They were able to. But now we're not able to do it as well with down to electronic. This might get noisy with my dogs here for a second, so hold on. My wife just got home. And they all love her. But there we go. Yeah, one that's been really taken up in the more, I don't know, recent years with the advent of electronics is the very bottom one, the tantalum oxide. You'll find that in a lot of the smaller little disc styles like this. But yeah, all these materials could be used, and it's like, yeah, see this oil, it's like oil. Did you know that all the transformers that are on the poles, right, bringing electricity into your home? Do you know that the inside those big canisters, there's a transformer inside there, okay? And you know what it's sitting in? It's sitting in a big thing of oil. And that's why whenever a transformer goes on a pole and you hear that big boom, basically what happened is it shorted out through the oil somehow, and that oil literally is igniting is what's happening. It's like, oh my God. And that's why you hear such a large explosion with those. Sometimes it's like, oh, but yeah, oil can be a good insulator, a good medium. Doesn't go so well in packages, but uh, so really that's what, chapter 15, like I said, it's really looking at, okay, how do we rate these things? What kind of materials are they made out of? So it's good to know, like, okay, these styles are this, they're made out of that, and whatnot. they all pretty much work the same. The only ones that are like polarity dependent are the electrolytic styles, like all the smaller, oop, go back here, like all these other styles like this, they're not polarity. It can go either way. It doesn't matter. But see on this bottom one, right? See how it's got that, you got a plus side to it. That one is important as far as polarity. So if you reverse it, no, well, no, it just depends on how large it is and what kind of voltage potential we're hitting it with. But anyway, so yeah, see how he says here they can be connected to a circuit without regard to polarity, except for electrolytics. But electrolytics, you'll even see on there, and they even have two different lead lengths. So one side is that I generally have it drawn with a stencil where it'll show the minus side to it. So always be on the lookout for that. Well, we'll go through that in the lab tomorrow. But yeah, the very bottom one is the important one for us to remember. Okay, this is the ideal property of capacitors. They block DC voltage and pass AC voltages. Very important for later applications. And it's like, really? And it's like, oh, yeah. Yeah. So in certain cases, like, well, you'll see later on, like in 134 and 135, that blocking the DC out can be very important for some circuitry and allowing the AC to go through. But we'll get into that in another semester. So the most commonly used ones right here, the micas, the little round disc ones, right? Mica, mylar, paper ones are cheap. Some years ago, now this is an interesting thing, but the type of paper you use can be important. Um, in the late 90s, uh, we got a lot of our like capacitors and stuff are made overseas, okay? Different Asian countries. I'm not going to point fingers at any particular ones, like Taiwan and Japan, but no. um, so if you look at the late 90s and early 2000s, a lot of electronics were experiencing premature end of life cycles for their products. And what happened was they were using inferior paper, and so these capacitors were literally breaking down. The rest of the circuit was fine, but the capacitors were literally breaking down on these boards because the material that they were using was junk. They weren't even lasting because typically on the shelf electronics should last 5 years. Okay, off the shelf, you should have 5 years of life out of those things. Um, and usually when your appliances die these days, it's primarily due to electronics. Okay, some of these like old appliances lasted forever. Yeah, they didn't have all these fancy digital electronics on them. And primarily what fails the most when I was in a repair center is the capacitors. We would have repair kits for these things, and what we would do, I swear to God, the first thing you would do when you get these things in, recondition them, basically replace all the electrolytic capacitors because of the paper material breaks down over time and degrades the capacitor. The micas over time do hold up a lot better, but you generally, like I was saying earlier, the electrolytics have a much higher rating for voltages and such, where mica and the films, we can't really get them into that higher voltage rating, and that's why we still use the electrolytics just because of the large voltage potential. But anyway, so ceramics, and then yeah, the new styles, the surface mounts, right? SMT technology, which is more and more, what we have today. It's how we got our cell phones. You open it up and all you see are these itty bitty tiny components, just surface mount. Meaning that it's deposited on the board and not through. See, the components that we've been primarily using in the breadboard, that's through hole technology, which is the older style electronics. But now for spacing and whatnot, we've been going to surface mount more and more. Smaller board sizes, smaller component sizes, and there's even different levels to SMT. You'll find they actually have rating numbers, and it depends on like package sizes. But anyway, so the kind of capacitors that we're going to more commonly see, as like field techs, field electricians, that kind of industrial electricians and everything, will be these styles. And why is that? Well, because we're going to be involved probably with some type of industrial machinery, okay? And so with that, this would be something that we would be looking at. You see how he's going through here and even have a diagram where we have a rotor involved. Dielectric in this case is going to be air. So these are very simple capacitors in one respect and can be kind of complicated at the same time. But yeah, as you basically rotate this shaft around, the flywheels right there, you're making the rotor plates mesh with what they call the stator plates between the two, and then you have basically what's in between them is, and it wouldn't seem like it, right? But there is, I mean, even between my fingers right now, there's still air there. My fingers aren't fused, right? But so that's how they look at that. So you have the dielectric material separated just by air and not by like an actual material in this case. So you'll see these, and then yeah, common applications in these cases, the tuning cap and radio receivers. Uh, and this one's are probably the most important one for us is the voltage rate. You never want to exceed it. I mean, the maximum potential of this thing is the maximum potential. If it says it's 10 volts, that's it. So if I put a 20-volt supply across a 10-volt capacitor, it's anybody's game as far as what's going to happen here. But and there's safety factors we can put into that. But in the beginning, in our early circuits, no, it's if we exceed it, it's going to break down, uh, and it can be amusing. But they usually have them fixed. If not, like in some of the styles, we actually have to go and look it up. But the rating numbers, like on the disc ones, and I'll show you how we'll read those and whatnot. What's the important material? Uh, but here we go, electrolytics. So like I say, I see how he says that's gauze. It does. It looks like paper mesh with like some kind of shellac on it, basically. But yeah, see, the electrolytics have a very thin dielectric film on the paper, basically, which is it looks odd, but it allows it to get very, very large capacitive values. In this case, like if I wanted that 400-volt. So then you have on some of the AC induction motors, they have a capacitor hooked in circuit with the motor to basically give it a quick start. So you have that charge sitting there. So when you start it up, it doesn't have to wait quite as long. It's got a faster start potential. They're electrolytics. And if you ever hear one of those go off, oh my God, if you're standing nearby, it's like a gunshot. It'll surprise you. But yeah, electrolytics, they are polarity dependent. So because it is that roll of paper in there, so the direction that it goes is very important. Otherwise, because if we reverse direction, it can't handle the way the charge is going across it, and it'll just cause the dielectric to break down, and then it's done. Okay, so yeah, and this is a disadvantage, is the leakage current. Caps don't really oppose current so much. They oppose or block voltage. The current always seems to wiggle its way by for some reason. So, but it's largely because of the way the electrolytics are. You got this mass storage potential, but because of that, at the same time, it's also not the best insulator in the world, so it doesn't work ideally. So if we were using like one of the mica ones or something like that, we wouldn't have to worry so much about that. But at the same time, we're not going to get a mica capacitor in a size like this. But yeah, and then the other style we got here, the tantalums, which they do use more and more. They are better than the gauze shellac paper styles. They do come you get a larger capacitance and a smaller package size. They do last longer because that paper does break down. That's why I always say, yeah, give it 5 years. Um, yeah, it has less leakage current. It's more stable dielectric, so it operates better. And ultra capacitors, these are, and in fact, they're doing more and more stuff with these lately, like, with the stuff with Elon Musk and Tesla and all that. They're getting into the fast storage batteries. This is the kind of thing that they're playing with, is these ultra capacitors. And a very cool thing about these is A, is their capacity, okay, how much charge they can store, but B, how fast they can store it. See on the very bottom, it says ultra capacitors can store an enormous charge and almost act like a battery. And in fact, if they can still continue, keep doing research along these lines like this, I can very well see that, like your cell phones and, the electric cars and so on and so on. Even like, it would be fantastic for like our hand drills and stuff like that, right? That basically these won't even really be batteries in the traditional sense. It'll just be one big honking capacitor that quick charges. So if you run out of juice, boom, pop it in. 5 minutes later, you're good to go and ready already. Okay, it's reached its full charge. This stuff is, well, you can tell I'm very excited. I'm a nerd, but so he does a little breakdown of it, kind of trying to show you, the type of material that we have here. So you have a separator, see how it's like all negative potentials on the one side, positive. So they've been playing more and more with this and coming out with different materials that act as these really strange dielectrics. If you actually see like a real true picture of it, it looks really weird. But yeah, this stuff. And in fact, like I say, over the next 10 years should probably be really exciting with this kind of thing, because they are going to make a lot of headway, more and more pushes. We could try to go to electric cars versus the old gas style ones. I mean, what, gas engines over 100 years old? Name one thing from 100 years ago that you still use today. Yeah, automobile engines. I'd say it's time for a change. No. But really, I mean, look back and look at technology and stuff like that from 100 years ago, okay? And how much of that, there's certain things we use, but it's been changed by like so much. And yeah, the gas engines changed a lot, but it's still running on gas. Hello. But anyway, but no, I expect to see a lot of really, really, really cool stuff with these things over the next few years with these ultra capacitors, super capacitors. I'm not sure what the end. Oh, I've been going all the way through here. Huh? So it's kind of like how he wraps it up, talking about properties and things like that with capacitors. But yeah, it's pretty exciting stuff overall. See, essentially, ultra capacitors, and they don't look right. They're modular made. Like I said, they look more like batteries than they do actual capacitors in like the traditional sense. But I can see these things taking off quite well. It'll yeah, ultra capacitors, so like, you could store your thing and have it hooked up later. It'll act just like a battery. It won't lose its charge. And unlike the smart batteries, like the lithium ion ones we use, where over time the battery just degrades and you just eventually becomes junk. Well, these won't do that. Very interesting stuff. But we won't get a lot into this. I mean, it is interesting, right? Yeah, products of memories or clocks, but overall, yeah, electrical vehicles, I'm telling you, you're gonna see them on our power drills and whatnot. It'll be pretty neat and lightweight too. That is the other cool thing. Okay, now there is some stuff that they can play with, depending on our hookup of capacitors. If we go series style, parallel style, series style. Well, we'll get into that in a little bit, but how to think of this? There is, there, 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 A very simple capacitor is a length of wire. Okay, and depending on the length, how long it is, or how short it is, and whatnot, is how much capacitive ability it has. So it depends on how you have the wire in place in the circuit. And in fact, in some of the early like radio electronic days, vacuum tube technologies, your capacitor very simply was a, a piece of wire. It was, made of a specific size and a specific length and everything, but it still acted as a very, very simple, very basic capacitor. And it worked very much like in this diagram that we have here. So how, let's see, basically, how does it do it? So you can see by his diagram here, so we have like these two laid out and they're in a parallel style configuration, okay? Um, Trying to think of a good way to do this. But yeah, and see, it's all based on length, and we'd have to get into some of the formulas involved. But a real long section of cable, if we've done it right, it can have a good storage potential to it. Not for very long, right? It's like more of a quick style thing. It's a cheap and easy style capacitor, but this this effect can happen, and if you're not careful, sometimes you can actually introduce a parallel capacitive effect into a circuit without realizing it, and then sit there and go, "Oh, what the heck is wrong?" And it's like, "Well, you made a capacitor," and it's like, "Oh, wow." And it's just something, something to think about as technician. Run into some strange things out there. uh, but in this case, yeah, you see it stranded together like that. Um, Way to look at this. So I got two different wire sets running like this, right? Um, and what's acting as my medium in between there? It's air in between. But the one, and they call it crosstalk. Basically, it's like noise interference. But what's happening is you've got to imagine as the step runs through these wires, okay, if we're dealing with signals and AC, you're making EMF. It's got a wave going through it, so it's like pulsing as it goes through these strands. Okay, the electrons are flowing, but we still have electromagnetic effect going on. And if the other wires are too close, okay, that electron, they get in the field, and then the two fields intermingle, and the two signals end up like meshing. And see at the very bottom here, it's like this crosstalk. So our input one looked real nice and pretty, and then look at this garbage, and all that was happening is the capacitive effect in between these two. And in fact, one of the things in residential, right, it's a code thing. All media cables, like if you had like cable line or telephone lines and whatnot running through your house, have to be 48 inches away if you're going to run like parallel. Let's say I got my AC lines running up to to the crawl space up in the top, running down, like snaking down the middle of the house, right? And then I decided, oh, I'm going to put my cable and telephone lines and run them right with them. No. The AC EMF will literally garbage out your cable transmissions, your telephone ones. So it's actually NEC code 48 inches, 4 feet away if you're going to run them parallel like that to get rid of that crosstalk. But yeah, it's a capacitive effect. It's like literally where we've used a piece of wire like that. And sometimes, like I say, in the early days, they did do something like that. But you can have this happen inadvertently, even in a factory setting without realizing it. It's like, and you go, well, what's happening to my signal? And it's like, there you go. And it's just one of those odd things, but yeah, crosstalk. And it's a capacitive effect that goes on here. But anyway, so really the nitty gritty of this chapter was what capacitors are, what capacitors are capable of, what they're made of, and this and that. The thing we get down here, this is the actual formulas involved with this and whatnot. where if I have, all right, let's say this, I have several capacitors in a parallel configuration, okay? The formula is as such. And it seems strange, okay, because it's not like it's not resistors. So in resistors in parallel, we had to do a particular formula to get what the overall resistance was, right? Well, capacitors in parallel add up. And then to really mess with your head, capacitors in series are done just like we did resistors in parallel, where they don't just add up. You have to literally do this. You get your capacitive equivalent. Let's say I had, I don't know, 3 different capacitors on the series configuration, and I wanted to find out what my overall capacitance is in the circuit. I would have to do this formula. But if I did 3 capacitors in parallel in a parallel configuration, right? All I have to do is just simply add them up, 1, 2, 3, and that's it. So we're gonna like parallel a lot more than we like series as far as this part goes. But no, but yeah, it's a strange thing. And I'll have a, I think I have the formula sheet, but we'll have a formula sheet for that. Basically showing how to do capacitors and how to do inductors, in series and parallel configurations. So part of this chapter, yeah, we're going to start looking at series and parallel type configurations. And from a DC standpoint, from the beginning to help us understand what capacitors are doing and get comfortable with them. But and that's the end of the chapter. Really, is like the parallel and series configuration. So it's a simpler math. And like I say, it's just think of it as opposite of resistors when you want to do overall, like how much capacitance does my circuit have? And so, and that'll end the chapter. And there'll be, of course, there's going to be homework questions for it, right? Right, of course. No. But really, that's it. That introduces capacitors. And then from here, the next chapters. So next week we'll be looking at the next 2 chapters deal with capacitors. So now we know what capacitors are, right? And now we're going to learn what capacitors can do. Got to have my caffeine, but really that's it. Let's stop. We will stop sharing that screen so you don't have to stare at. You can stare at my ugly face instead. Yay! But no, and tomorrow our lab is it's gonna be pretty simple. DC, we're not gonna really be playing with AC or anything with it yet. And so that way, we'll just do something simple like, okay, how much capacitance in this circuit and calculate it. And we'll go ahead and slap the meter on it and measure it and see if you're able to figure them out right or not. Right. That's what we do. But so that'll be fun. It won't be real horrible. Horrible is next week. No. But I'll assign that homework sometime today for chapter 15. And like I say, it'll be due next Monday. And the quiz on it'll be these are all going to be pretty much combined quizzes. So your quiz on Monday will be chapter 14 and 15 combined. Probably about like, I don't know, 20 questions or something like that, based on the homework. So if you go over all the homework questions and whatnot, over the weekend, you should do pretty good on the quiz. Um, but that's the style we're gonna do. Yeah, two chapter combinations, and then quiz on Monday, I think, for the next several weeks, right? But so tomorrow's lab, like I said, it'll be fairly simple, and we'll just be playing with capacitors. So make sure you bring your kits. If not, I do have. I have to check. Yeah, we have quite a few capacitors. I don't know if it's the same the kits or not, but we'll be able to play around with that. But other than that, that's really all I have for today. I don't have anything fancy. We'll have, like I say, I'll have the homework posted today for chapter. Dog, what are you doing? Chapter 15, and then the quiz on Monday, and then tomorrow 9 o'clock, right? 108. And we'll do our first capacitor lab, and that's about it. Unless you guys Anybody have any questions? We going through okay? Chapter 14 wasn't hopefully isn't horribly painful. Well, I know everybody hasn't looked at it or anything yet, but but that's what I got today. That's it. Introducing capacitors and what they are, and then we'll start playing with them. But other than that, that's pretty much it for what I have today, guys. Oh, this silence, it's killing me. Oh. But now, you guys all good?
Yep.
Awesome.
Yeah, I'm good.
All right.
We're good.
All right.
Good.
Well then, gentlemen, I guess I'll see you tomorrow morning at 9 o'clock down there. And,
All right. See you tomorrow.
all right.
Sounds good,
Bye.
Tom. See you.
Take it
See you
easy.
tomorrow.
See you tomorrow, Tom.
All right.
See ya.
Bye.